Yeah. And then we'll start up the lecture. Okay, so ultrasound. We took a look at ultrasound in the introduction, obviously. This is a page that gives some links to echocardiography systems, which is a one application of ultrasound. But if you just go into Google and Google, ultrasound imaging General Electric, or ultrasound imaging Philips, ultrasound imaging Siemens, they'll bring up their commercial page that describes all of their systems. And it's usually worth doing because they have the state-of-the-art images. The best images they can create will be on that page. And so it gives you, it's like a Guinness Book of World Records kind of thing. It's the extreme of successful imaging, is seen on these pages. There are many ways that ultrasound images fail, but when they work really well, it's pretty spectacular, right? So it's worth seeing that, the spectacular stuff. I'm just going to review some of the things that we looked at the introduction to imaging to go back, because you've probably forgotten it. So we're going to look at 2D ultrasound. In cardiac, it's called echocardiography, and 3D echocardiography. The time to acquire an image, as you can see here, is very short, right? So this is a 2D image, and we're getting them you can get them up to 30 frames a second, and even faster in some of the more advanced systems. Okay, so I have one single plane inside the patient, and I'm making images of that plane 30 times a second. And so it's right up at the limit of your visual acuity to look at changes in time, right? I think your eyes are probably only at 30 frames a second, somewhere around there. You can actually, that your eyes are sampling with a specific sampling rate, because when you drive on the highway and you look at other wheels on cars that have spokes, you'll see sometimes the spokes will be slowly moving backwards, or they'll be stationary or slowly moving forwards. And that basically aliasing tells you there's a beat frequency between your sampling rate and the rotation of that object, right? And so if you say, oh, I'm going to do 100 frames a second, when you put it up on the screen, you're not going to see anything different than you did at 30. A little bit, you might see sometimes when you play things fast, it's almost like another dimension pops open, like you go farther into a depth perception when the frame rate goes up, which is kind of interesting. But 30 frames a second is usually enough for a human. Now, if you wanted data at 100 frames a second, you can always go back and click through frames and make measurements, right? And that is truly at 100 frames a second. So now I'm just going to click frame to frame, do a segmentation on, say, a valve leaflet, and see where that leaflet moves in that 100th of a second, right? So that's achievable. The voxel volumes, they're moderate in terms of spatial resolution. You can make high resolution ultrasound if you, as we'll see, if you have the transducer really close to something, like say a vertebral artery, you can place a transducer right on the artery. And so the stuff you're imaging is like millimeters below the transducer, and you can make higher resolution pictures if you're close to the transducer. As you go to depths inside a whole patient, like inside the chest or in the liver, at those depths, these are the voxel dimensions that are typical, right? It's 3 millimeters by 3 millimeters. To do you can imagine doing a 3D ultrasound image. If I can get 100 frames a second in a 2D image, then what I should do is get 10 frames a second in 10 different slices and sweep those slices back and forth. And now I have a 3D image, right, at 10 frames a second. So that's essentially how 3D ultrasound is done. It's just, you just raster through two-dimensional planes in some order. Right? And, you know, in comparison with the other techniques, you know, it's much higher resolution than nuclear. It's about the same as 3D MR. You know, MR gets one resolution dimension for free. And so you have one dimension that's usually high. Doesn't touch CT, but CT, you know, takes 140 milliseconds to get the whole volume. It gets the entire volume though. So, you know, there's a trade-off there. So again, this is a review. The basic setup is this machine, and they all look about the same. Like when you line them up and say, oh, which one should I buy? They all pretty well look the same. And it's hilarious when you go into the commercial site to look at the different models. It's almost like buying a car. They say, oh, look, we put on the side, and they'll have some feature over here, and it's a gel warmer. It's like a coupling gel warmer. It's like a cup holder, right? Say again. Okay. Okay, there's a question here. I think, is it not being recorded? Did I not push record? You're sharing. I think it's being recorded. Isn't that what this little blinker says here? I think it's being recorded.
I think that was from previous, Professor.
Well, it says now my options are stop recording and pause recording. So I think it's being recorded, right? It is recording, so, okay. May I ask what the general frequency rate? Yes, we're gonna get to the frequency range of transducers. Okay, we will get there. We'll know in detail what those frequencies are. Okay. All right, so here's the basic system. They range in price from tens of thousands of dollars to many hundreds of thousands of dollars, depending on the quality and sort of features that you get. This device here is called the transducer, which is held by this person who is a very highly trained, experienced ultrasound tech. And they place the transducer on the patient's body and then image what is underneath the transducer. And these images come up in real time. They adjust certain parameters to change the image, like focal depth, slice thickness, you know, frame rate, Doppler on, Doppler off, all of these kind of things. They do all that adjustment in real time with their hand. And then they usually have a bar here where they sort of capture, and they'll capture and record short snippets of video, or they'll capture and record single frames and then make measurements right on those frames. And that goes into the report, right? So the tech is responsible usually for also making geometric measurements. So they get the right view and then they stop, take a picture, or they'll sometimes take a video and then they'll go frame by frame to the right phase of the video and then make a measurement. So let's say they'll make a measurement of the diameter of the left ventricle, or they'll make a measurement of the head size of the fetus, you know, or other, you know, length dimensions of the fetus. And then they say, you know, save that, and it goes into a folder that has many, you know, captured videos and measurements and things like that. And so that can vary from site to site, you know, how they put that together. But the interesting things, this machine, the quality of this machine can also vary a lot, right? So go to your doctor and you see this rickety old ultrasound machine and they're making these pictures, you can ask them, like, what is that model? You know, ultrasound machine. That's not a Sequoia, yeah, right? So, but most people wouldn't know the difference. So they get really small, obviously, because, you know, electronics is really small now. And so you can have this transducer, this thing fits in your pocket. You just walk up to the bedside, and if a person has crushing chest pain, you can look at their heart and say, well, let me see if your heart's still beating, right? You can imagine this would be a great thing in the field, right? If you're out in a place that doesn't have great hospitals and things like that. And there's extensive training on how to manipulate the transducer with your hand such that you get the correct imaging planes. And given that you have one imaging plane that is correct, say here where we have, you know, basically this is called a parasternal long axis view. And then you want to get this one, and you're already here, there is a way to manipulate the transducer such that when you rotate it, you land on this plane. So that is a real motor skill, right? That's something that you learn about through practice and things like that. You can't really write it down as a prescription and have somebody figure it out. You got to practice. You can see the characteristics of an ultrasound image. It's kind of noisy, right? It's a little bit confusing unless you know what you're looking at, right? Because it's not an anatomy book drawing, right? Some CT images and MR images, you know exactly what you're looking at because it resembles the anatomy so much. This isn't as much. The transducer here, you know, sends out chirps of ultrasound, and then it also works as the echolocation device, it's like a receiver or a microphone essentially, and it picks up reflections as they come back. And this is the field of view over which that occurs. And here's the location of the transducer is up here. We're going to beam ultrasound energy down into the patient, and it'll reflect off surfaces back here. We'll see this in detail. You can see a couple of immediate things, like just from looking at these two pictures. Everything looks, the spatial resolution of the picture up here, these little dots and things like that in this dimension look pretty sharp, but then as we go farther away from the transducer, everything looks like it's getting blurred in this dimension, right? Which is the case, right? So the spatial resolution is depth dependent, and we'll see how you adjust the depth of that. The operator of the system learns to see a picture like this, right? Which if you came in cold and you looked at this picture, you wouldn't actually know what is what, and map these features onto the true underlying features. Now, this is true of all, this is just a cardiac example, but in OBGYN, when you're looking at staging, you know, where a fetus is in development, a lot of that is the skill of the technician waiting for the right moment and getting the right plane through the fetus when the fetus is like moving around and sucking their thumb and doing this and that. You know, so sometimes they can coax fetus to move in a particular direction and get the right plane. In cardiac, the heart's not moving around, so other than beating, you hope. And so here's your transducer up here shooting down through the chest, and here's the aorta and the left atrium, the posterior wall of the left ventricle here, inferior wall. And so you have this kind of model in your head when you're looking at this picture and to make sure you're in the right orientation. So this is called the parasternal view, where the transducer's up here compared to this model coming down this way, and that's what it looks like. You can see as you move away from the center part, everything fades away. And then if you put the transducer below the patient's rib cage towards their feet and look up towards the heart, you can get a horseshoe looking object, which is this. This is the left ventricle. And then the two atrial chambers are back here, right ventricle's here, and you can see the valves. If you want to look at the orthogonal view, so we've got all of this heart wall now imaged, but I don't know what's happening out of the plane. So I just rotate by 90 degrees and I get, so if I intersect this volume here, I look at this picture. Actually, you intersect it sort of here. It cuts through the left atrium, central part of the left ventricle. Here you see this, and then there's the left atrium. So you move around. Each one of these classic views you'll record, right? And then when the physician takes a look at this, they're usually not in the room when this is done. They're in the back room reading these cases. And so it comes across their workstation, and these movies are all loaded up, ready to go, and they just cycle through them, right? And take a look. Normally, if the tech is good, they don't have to go back and say, oh, we missed something. We should have done this view, that view. The tech will adapt to the situation. So looking at those views, these are all called long axis views, and they all have this horseshoe orientation, right? Where the apex of the left ventricle is visible. You can rotate the transducer 90 degrees. Instead of going along the long axis this way, you just take it in your hand, rotate it, and you'll cut through the heart this way. And you can just tilt up and down and take a look at different levels through the heart with these donut shaped things. And these are called short axis images. And in these, you can imagine in the long axis images, remember we cut this way and we cut through, well, we basically cut through this way. You know, for the 4-chamber view, we cut through this way, and for the 2-chamber, we cut through this way. So you're really only seeing 2 regions of the myocardium. When we rotate 90 degrees, we now see the entire circle of the myocardium, and we're able to look at the motion of that circle. It's like a ring in which the inner diameter of the ring, you know, gets smaller as the blood gets ejected, and the wall gets thicker. This usually happens in a very concentric and synchronous way, right? So when you're watching it, it's just like a donut that basically the hole in the donut gets smaller and then bigger and then smaller and then bigger. And it happens equally around each angle. When that doesn't happen equally, when one of those angles looks weird because it's not getting, the heart wall is not getting thicker, it's a hallmark sign of the myocardium not performing well. And so that's how you detect ischemia, i.e. a lack of blood flow at that location, is that the heart wall muscle itself is not contracted. And so normally the tech will get a mid view, a base view. Here's look at the valve planes, and then move the transducer and get apical views as well. Right? And so that sort of samples the whole object. Here's some examples, right? They look much better as movies, right? Ultrasound just looks much better when you watch the movies, right? Because your eye tends to average out, you know, the static noise on each frame as the movie passes by. And you're also distracted by the really amazing resolution of things like the valve, you know, opening and closing, right? And so here, you know, you can, what's often done to try and get a objective measurement of what the ventricular performance is, you'll draw these contours. So this is a contour line that has been drawn at each time frame with the guidance of a human. Okay, so the human draws these contours. The image will, as we saw in segmentation, remember with the CT, we can have an algorithm running underneath that says, well, I'm not going to go past this because there's a signal barrier here and I'll stop the contour from growing that way. In ultrasound, that's really tough because the signal itself has fairly low signal to noise, right? And so you'll find a lot of errors if you just let it go automatically. So humans are a big part of drawing these contours. And it doesn't work worth a damn for figuring out what the change in function is. If you're looking for a small percentage change, like 10% or something, you can't see that when you draw these contours, because you get 10 people to draw the contours, you get 10 different answers. Right? So what is done mostly is experts look at the movie. They don't bother drawing contours and stuff. There are people here at UCSD, like Dr. Tony DeMaria and people like that, who probably looked at 100,000 echoes, right? And so they, like, when they just look at the movie, they just know what's happening, right? They've seen it before, they know what's going on. Their deep learning set is huge, right? And so they've iterated to being able to see it. I trust that way more than I trust people drawing contours. Is an expert looking at this going, you know, this heart doesn't look great. This looks like this person needs attention, right? And so a lot of ultrasound is often used as the criteria for applying a certain therapy. And it's usually based on ejection fraction. And that is, if your ejection fraction is below 35%, then you qualify for that procedure, for that intervention or therapy. And a number of therapies have a 35% cutoff in ejection fraction, which seems a little arbitrary, but it's not. It's like over history, it just seems that that's how it works out the best. And you know, I trust more a cardiologist looking at the movie and telling me what the ejection fraction is just from their head than I do somebody drawing the contours. I know that sounds ridiculous, right? But they're really good at it. You know, they look at it and say, this heart is a 30% EF heart. It's almost like they themselves have like a 20-point scale that they can nail. Like they don't bother about anything above 50% because it's all normal. If it's like below 20%, you just know that's really, it's in that sweet spot around whether or not they're transitioning, right? And they're very good at it. So I trust the human reads. I don't trust the auto reads. Now, we could do a study where we say have 1,000 CT absolute truth EF numbers, and then the echo done like moments after the CT, like on the CT table, and then just train up a neural net to do it, right? I think that's the best way to go with echo, as opposed to come up with some better ways of drawing contours, right? So I'm sorry, that's a long sort of diversion. So this says that this ejection fraction is 59% or 60%. Yeah, I don't know, maybe. But the other thing, and we'll take a look at this in detail, is this ability to look at the frequency of the signal that's reflected back to your transducer. And if the frequency is shifted up when the signal comes back. So what happens, we'll see, is you put out a set of pings, just like bats with echolocation, they put out little chirps. This machine puts out a little chirp, you know, maybe 2,000 chirps a second. And that chirp goes into the sample and then reflects back off each thing that can make a reflection. So you listen to those reflected chirps, and they're usually, you know, thousandths the amplitude of what went out. And if the frequency jumped up, right? So let's say we put a 1 megahertz chirp out and then it comes back and it's got a slight increase in frequency, then you know the object that it reflected off is coming towards you, right? If the frequency of the reflected signal goes down, that means the object's going away from you. and that's Doppler shift. So what you can do is, by the timing of the reflection of the chirps, you position where things are happening, and we'll see how that works. You can make a map of the velocity of the blood, because a lot of reflectors are in the blood. They're like the erythrocytes, the individual erythrocytes are echogenic. You can put tiny little bubbles as a contrast agent, like very, very small bubbles, micro bubbles that don't cause you any deleterious effects. They just, get absorbed. If you put those in, you get super echogenicity off those things. And so you'll get an enormous echo. So here, basically the yellow and red colors are things flowing towards the transducer here, right? And the blue color, black means there's no velocity. The blue color is stuff going away from the transducer. And here's where the transducer is in this patient. This is the apex of their heart here. So we've put it on their chest, and now we're listening to the echo signal. And the interesting thing is you can see that this mitral valve, this structure right here is the mitral valve. And then when the ventricle is contracting, there is a blue jet right here. See that little that comes through? And that is blood that is moving away from the transducer. It shouldn't be moving away from the transducer, right? It should stop right here, right? But what's happened is this mitral valve is not coapting perfectly well. There's a little hole there. When it tries to close, for whatever reason, it's not closing, and there's a leak. And you can hear that sometimes with a stethoscope, right? When you listen to the patient's heart, you can hear a little whistle or something going off as that happens. But here you can image it and figure out exactly what the peak velocity is and things like that. So this is Doppler shift. It's a very powerful component of echocardiography for detecting things like this, right? As you can imagine, you have very high sensitivity for detecting that. Okay. And then 3D imaging. It takes longer, obviously, to make a 3D picture because it's just a stack of 2D pictures. So however fast you can make a 2D picture, you just stack those together and you get your 3D. You can stack them to either stack them, or you could just take rotating. So if I have one 2D picture and I draw a line down the center of that picture and then I rotate it about that line radially, that's one way to make a 3D volume. Another way is just to start at the top and move down to the bottom of basically a cube and just make a 3D volume that way. So you can make ridiculously good 3D pictures when the object isn't moving too fast, right? So in OBGYN, when you're looking at babies, you can make these fantastic pictures because when they move, they get very distorted, a very distorted, scary look about them. Like, what is that? But when they're stationary, they look great. And so you get innumerable, really cute early pictures of your baby. And, valuable information about development, etc. We looked at this in the introduction. Again, this is all review. As we'll see, the construction of these transducers, there's a line of these crystals that vibrate at very high frequency along the transducer, and you can create them with different geometries. For instance, this one has this is a high frequency one. So this is developed for making really high frequency ultrasound, but I didn't put one in here that's essentially a square as opposed to a linear array where you make a slice and you tip the slice. You can also make a big square where you have independent elements on the transducer and focus the beam in 3D, right? So this one is cool. This is a ultrasound transducer right on the end of like a laparoscopic tool. So if you're in there and you say, oh, what the heck is that thing, or is there a vessel under here that I should really be worried about? And put this, just lay it right on the tissue inside the patient and say, oh, yeah, there's a big vessel under there. Don't pull on that thing. And then you come back out, right? So there's a whole bunch of these. So ultrasound is used, and then when we get to applications, I'll try and look up some great papers and videos on using ultrasound to direct both ablation therapy, if you're trying to ablate a tumor locally, biopsy guidance. So a couple of students from my lab, right after they graduated, they joined Philips and were essentially led a team to develop a ultrasound guided biopsy machine, in which they had these biopsy tools with these balls off the end, and they had cameras. So when you moved the biopsy tool, you knew precisely where the tip was from where those balls were in 3 space. And you had a ultrasound transducer imaging the volume. And you knew from the way the handle was on the ultrasound transducer exactly where that volume is. And so they could align both those things and then use the biopsy tool to hit the target. It could be a very small target and you would nail it right on. And then usually with those things, you suck out cells, right? And then take them to pathology and figure out what kind of tumor you have. So here's a diagram of the transducer itself, okay, just to get the coordinates. As we saw a bunch of these. So you have this, in this case, there's a linear array of these crystals. They're usually ceramic. And just to get our coordinates right, this is called the lateral resolution in this direction. Axial in this direction is the depth resolution. And then slice thickness is in this direction, or elevation, right? So the transducer itself has a natural slice thickness that when you put it down, it will just kind of focuses down at a certain depth and then broadens out. And then we can mess around with the structure of the array itself to modify this lateral resolution here. The axial resolution we'll see is a function of how far deep you are in the sample. So here's where the transducer would be. In this ultrasound image, we have 45 degrees essentially, in which the beams of ultrasound are swept across this sort of like a windshield wiper, right? So we have a single beam that we're going to measure our signal from. We're going to sweep that beam back and forth across the sample to create this picture. And that sweep across goes really fast, right? So you could, as we saw, we could make upwards of 30 2D images a second, if not more. Any questions about this basic geometry? Yeah?
Just the slice thickness, that's determined the voxel size.
It does determine one dimension of the voxel size, right? So back on our chart, I tried to put each dimension in because each imaging modality has different, relationships between the slice thickness and the in-plane resolution. So, for this, I think we saw it was about 3 millimeters, something like that. And that seems pretty reasonable, right? A 3 millimeter slice, and a lot of them are using 5 millimeter slices, something like that.
Can you shrink that?
Yes.
Make it narrower.
Absolutely, you can shrink that, and we'll see that. So the question is, can we, by doing some kind of shenanigans with the transducer, reduce the slice thickness so we get higher resolution in the slice direction? And the answer is yes. We can make, instead of just having a 1D transducer that is a certain dimension, we can break it up and make it 2D, and then phase delay some of these things to focus it in both the lateral dimension and in the slice direction. Right? So yes, there is a way to make that higher resolution. Oops. So basic ultrasound physics is the physics of the wave equation, right? It's essentially what it boils down to in Prince and Links. When you read their chapter on ultrasound, there's two chapters actually. There's the physics of acoustics, in which Jerry goes through the essentially the 1D wave equation, so just in depth as z, and looking at pressure as a function of depth, right? And so, it's just a second order derivative in space equals some 1 over c times a second order derivative in time, and then you solve that in all different ways. And so you can read that if you want. It's somewhat useful. But to really, to just the gestalt of what's going on here, it's a longitudinal pressure wave. Okay, it's not a shear wave like some kind of transverse shear or something like that. What we're interested in is this longitudinal pressure wave. And so if our medium was a spring and we just pushed one end of the spring back and forth at a certain frequency, you would see this is called an emergent property, right, of the spring. Is just like it compresses, and that compression just rolls through the spring, right? And we describe this with waves. And so it's this pressure or compression that is the thing that we're interested in. That's our signal, right? And what's going to happen is it will come down, and if there's something here, it will reflect off this surface and come back through the spring, right? Our spring in a human is the tissue itself, right? We're going to compress the tissue, and the simplest tissue is water, right? So we could do this in water. You could make a pressure wave go through water and come back up. You can do this in air, obviously, which is how we talk. And then if you go to really hard things like bone or say metal, you can do it in that too. And what happens with all those different materials is the speed of sound changes a lot, right? It's dependent on the material. And so the speed with which that wave goes through changes a lot. Also, the amount of decay of the amplitude of this pressure, as it's rolling through the spring, it's heating up the spring. And so the amplitude will decay away. And so you get this depth decay. This can be described, it's mostly described one solution, right? For the wave equation is a sine wave. It's a nice solution. And however, sine waves probably, as Jerry says, sine waves probably don't occur in nature because they're infinitely differentiable, right? So it's a nice approximation, but it's probably not what's actually in there. It's close. But we'll see when we go to some advanced topics of this that what actually happens, interestingly, is that depending on the peak pressure, the speed of the wave is different at different peak pressures, right? And so the wave itself starts to distort because it's not a perfectly linear process. But we're not going to think about that until the next lecture. Okay. So if we're just sort of to first order modeling this, we say, well, if I freeze time and I look at my medium, I'm going to have a high pressure part, zero pressure, so I'm back at my equilibrium condition, and then a stretched part, right? High pressure stretch, high pressure stretch. Okay. Any questions about that wave? Let me pop this up here. Okay, that was okay. Nope. Okay. So we have the speed of sound in the medium, and it's just the wavelength times its frequency. But it really depends on the material, and there's a couple of ways you can model it. But in the Bushberg book, and this is pretty simple, where you have the compressibility of the material, or the stiffness, measured as the bulk modulus, right? And then the density of the material, and this relationship, you know, the compressibility over the density gives you the speed of sound in that material, right? So if you have something that's really soft, like a really lax spring or something like that, versus a really tight spring that's hard to compress, it takes a lot of force to compress. When you push a wave down the very soft spring, it will move at a certain velocity, and when you push a wave down the tight spring, it moves a lot faster, right? So that pressure wave just shoots down. So you can imagine also if I put a ping in water versus a metal bar, I go ping on a metal bar, it travels down the metal bar really quickly, travels through the water much more slowly, right? And so you basically, you know, have this approximate relation to describe what the velocity is going to be. And then we can look at the densities of material and some of the stuff that we're interested in imaging with this ultrasonic pressure wave. And here, these are worth remembering, a few of these numbers, like water, soft tissue, kind of the same thing. 1,500 meters per second, right? Air, 330 meters per second. You should have those numbers in your head just for the heck of it. Right? If someone says, what's the speed of sound in air? It's 330 meters per second. Right? Does anybody know what it is in another set of units? No. Well, sometimes if you watch exciting movies about pilots, they'll break the sound barrier. I'll tell you what, it's usually in miles per hour. And what's, anyway, okay. And then down here, you know, in bone, it gets up to 4,000 meters per second. So this chart is good to know, especially these things here. Lung, it's a little bit faster than just pure air because there's a combination of spongy stuff in the lung. Okay, so here's just an example problem of figuring out, you know, at a specific frequency, you know, what's the wavelength of a sound wave in tissue, right? And it gives you an idea of like, what frequency should we use to make an image with sound in tissue? And you can imagine that you want to use a pressure wave that has a wavelength that is on the order, or is on the order of the size of the thing you're trying to measure, right? Just, you know, from just gestalting it, right? If you had a wavelength that was like 5 centimeters and you're trying to measure things that are really little, then you're going to have a problem on your hand. So this shows just, you know, using that table and the frequency of sound, say a 2 megahertz beam versus a 10 megahertz ultrasound beam. The 2 megahertz beam has a wavelength of, you know, about a millimeter. Then down here, we're at a 1/6 of a millimeter at 10 megahertz, right? So now we've got pressure waves that are really on the order of some of the things we're trying to measure, like a vessel, you know, like, is there a vessel there? Or is, you know, the mitral valve in the heart, or something like that would be at on that scale, right? So this shows you the question, the earlier question is like, what frequencies of sound are we talking about here? It's like, it's not just above the, you know, the ability of humans to hear, which is the definition of ultrasound, right? So what's the highest frequency humans hear? Does anyone know? Anybody know online? Nobody's an audiophile. Nobody, yeah. You got it, 20K. That's a good guess. So if you're an audiophile and you buy speakers that can do, you know, 60 kilohertz of sound, it's kind of a waste because a human can't hear that, right? They hear about 20, they get up to 25, something like that. And then as you get older, your ability to hear high frequencies is the first thing to go, like it diminishes. And that's why old people oftentimes ask you to repeat yourself. I ask people to repeat themselves all the time, partly because they're not interested in what you're saying, and partly because they can't hear the high frequencies. And so we're all, they don't have any consonants which have sharp clicks and pops, which are all high frequencies, right? When you take all those when you take the that out is right, and so you can't hear it. So, however, we're way above that with this. We're up in the megahertz, right? So, 1 megahertz sound wave, that's kind of an interesting thing, right? It's, is it sound anymore? Yes, it is. It's a pressure wave. And 5, 10 megahertz, and they go up to, some of these systems go up to 30 megahertz, right? Okay. Okay. Well, we wanted an introduction to acoustic impedance in terms of reflection. Okay, here we go. Okay, we're going to ask the question. Okay, so the way ultrasound imaging works is you send out a sound wave like a chirp, and it's very short. So it goes ping, goes out, and it's like 1 megahertz of sound, but it's only, a couple of microseconds long. That travels through the medium, and then it hits a reflecting surface. And what comes back is a reflection of that thing, and you measure that signal on your detector. So the question is, like, how much gets reflected? What would be a reflector, right? You can imagine that if there's, say, a vessel running, I've got a liver, and then my sound is going through liver, and then it hits a vessel with blood in it. So there's some kind of, surface there that we're going to change how the sound transmits through those two different materials. When you have a change in that, so if I have, the liver tissue and then blood in here, that change will cause a reflection, right? And so if I more simply, if I had a vat, and in the vat I had, say, Jello at the bottom of the vat, and then I put water on the Jello, right? When I put sound waves in through the water, when it hits the Jello, some of that sound will transmit into the Jello, and some of it will reflect back, right? And the amount that reflects back is proportional to the difference in basically the impedance or the resistance of the sound in the medium, right? So if I have a really loose spring, like a floppy spring, and I attach a really stiff spring to the floppy spring, so now I have one contiguous, one-dimensional spring. Half of it's really stiff, half of it's really floppy, okay? When I put a pulse, pressure pulse down that spring by just quickly, shaking the end, you will see that wave go down the floppy spring. And when it hits the really, stiff spring, what happens? Say again? When it gets into the stiff spring, it takes off and goes faster. But what else happens? Just by when you're a kid playing with stuff, you see, it reflects, right? It's almost like this, the stiff spring is almost like a wall, and it pushes a pulse back through the soft spring. So a fraction of the energy of the pressure wave gets reflected back, and a fraction goes forward into the stiff spring. This is the essence of how we're going to make pictures. We're going to have all these different interfaces of tissue that have different impedances, and each time our wave hits that interface, some gets reflected back and some keeps going. And it's good that some keeps going because we want to see the interfaces beyond that too, right? So it's basically you get a series of reflections as that wave is passing through the different media, right? And so the difference in acoustic impedance is what is causing this reflection or transmission. If the acoustic impedance of the two media are the same, then nothing gets reflected. It just keeps going, right? So if I have a floppy spring and I attach a floppy spring, it basically just keeps going at 100%. It's when that spring constant changes that I get the reflection, right? And you can model that as a reflection coefficient, and it's basically the intensity of the energy that is reflected, right? So it's the square of the amplitude, the intensity, right? And so here's the formula for how much energy gets reflected. It's if I have the incident is medium 1 and it's going through and into medium 2, it's the difference between those two coefficients over their sum, right? And when you run these numbers for essentially, when we look back at these acoustic impedance values for different tissues, you can then calculate what you expect the reflection to be, right, at these different interfaces. And so here, if I have, when I put my transducer on somebody's chest and they have a layer, say 2 inches of fat, and then it's going to hit a layer of muscle, we're going to see a large reflection coefficient there at the fat muscle interface. So how much is reflected? Well, these are the difference between their acoustic impedances. So we plug it into this and we get 0.015, right? So it's not much gets reflected, right, with these acoustic impedance differences in humans. So we're down to like 1/100th of close to 1/100th between that and a 50th of our original amplitude that we put in to the patient that will be coming back towards us, right? Okay. And the other factor is that these pressure waves, because they're causing motion in the material itself, so the material is squeezing down and moving apart as the pressure wave goes through, that will cause the material to heat, okay? And that heat is energy that is lost from the pulse, right? So if I have water, say, or some uniform material, and I start a pressure pulse with a specific amplitude, we'll just call it 1 in some units, right? And then I look at the amplitude of the pressure pulse as we move down deeper and deeper into the sample, right? And this is, say, centimeters. I will see that the intensity drops as I go down, okay? And it's modeled essentially phenomenologically. I'm not sure there is a great first principles model to say that this is a first order, decay with a mono exponential. But when you make the measurements with detectors in the material, you can just model it with this mono exponential decay, and you come up with a decay value that is particular to a material. However, it's not just particular to a material, it's also particular to the frequency of the ultrasound, right? So you can imagine that if I'm vibrating, things at a much higher frequency, right, that my amount of energy that is going to get deposited as heat might go up, right? And that is true. And so you get a much dimmer amplitude at say 1.5 at 10 megahertz than you do at 2 megahertz. And so this depth of penetration is something you have to take into consideration when you're picking a frequency to use. Like, how deep do we want to see into this patient? Normally these things, this coefficient is normally given in decibels per centimeter per megahertz. Right, so we'll have a chart of these for different tissues and different frequencies. Well, if we assume it goes linearly or inverse linear with frequency, we'll just, which is an approximation, but anyway, just put it in here. We'll have a chart of this for different tissues, right? And so you should know what decibels are, right? But everybody's in engineering, so I'm pretty sure probably you've come across it in other courses and everything like that. But they put this chart in here, which is a good idea. You know, it's just basically the log of the two intensities. And then, so you don't have to use decimal places, you just multiply by 10, and you get the dB of the intensities. So 60 dB is a factor of 1,000,000 reduction, right? And 3 dB is a factor of 2. Okay. So if you just look at the numbers that we have at a 5 megahertz ultrasound wave traveling a round trip to a depth of 4 centimeters, right? So it's in the liver, it's reflecting from a little pocket of air in the liver. So they're assuming because the change in impedance is so high that the entire thing gets reflected back, right? And it's down at 4 centimeters. So the round trip is 8 centimeters, right? So that wave, when you ask, well, how much is it going to have decayed through just loss of energy? You have to take it through 8 centimeters to do that. And then the total attenuation is this value, I guess, is given for liver in a table somewhere. We'll get that. And you find out that, the intensity of the incident over the echo is like a factor of 100. Right? So now we know how sensitive our receiver has to be for something that's 4 centimeters deep. We're going to be dealing with a factor of 100 difference in amplitude from what we transmitted. And so if your receiver, if that's below the amplitude your receiver can detect above, say, baseline noise, remember the Rose criterion and all that, so we need that signal to be sort of 5 times the no background noise or whatever. If that's not happening, then what do we do? We just turn up the gain on the transmit. It's like, make it louder, turn it up to 11. So we just increase the gain on the transmit, and then it'll give us an increase in what it is received. But we can't do that forever, right? Because one, we probably just have, a peak gain that our crystal can put out in terms of peak amplitude for ultrasound. Secondly, we're going to start depositing energy in the patient, right? And you can actually perform therapy with an ultrasound transducer by turning the gain way up and turning the focus up. So that if you focus down on a small volume, say 1 cc of tissue, and all the ultrasound energy goes on that 1 cc of tissue, using a specially designed ultrasound transducer, you can heat the tissue up to a considerable amount. And this is used for debulking tumors, right? And debulking benign processes a lot, right? So therapeutic ultrasound. Yeah,
give it lower frequency.
yes,
To use a single device.
you can do that. So if you're not seeing stuff at the depth you want to see, you just drop the frequency, and then stuff comes into view that's deeper. Yeah, exactly. So the way ultrasound is made at these very high frequencies are with these piezoelectric crystals, and they're, the molecules in these crystals, they're a ceramic, are usually, they have an alignment, a natural alignment, and the elements that are aligned are actually have a polarized charge. So when you put a voltage across the crystal, these elements of the crystal will shift and they'll change their alignment. And then when you reverse polarize them, they'll shift in the other direction and change their alignment that way. So you can put this voltage signal across from positive to negative and make the crystal oscillate, essentially. And you can essentially just adjust the frequency as you wish, right, to get this going. And so you can see probably the amplitude that you can achieve with these is going to be limited, right, by whatever this throw is, in terms of the strain on this crystal. Well, it's kind of patently obvious what's going on here, right? Is that this thing is getting thicker and thinner and thicker and thinner, and therefore the pressure wave is coming off the front of the device. So a transducer, here we have a linear array and a phased array. If we look at the linear element, here's the crystal. This is its, this is its depth, like perpendicular to this surface. And so we're going to put a voltage across here, and and the crystal will vibrate, if this depth is the Z direction, the crystal will vibrate in the Z direction. And we'll stick a whole linear array of these crystals along the face of the transducer. And in the most simplistic way of rastering through to get a two-dimensional image, we'll just temporally raster across this crystal, and we'll make a 2D picture just by changing, the position of the focal point, right? More commonly nowadays is these crystals are arranged, and there's electronics in here that change the phase of the vibration of the crystal depending on its position in the array. So if I start the crystals out here and out here slightly earlier in their pushing in than the crystals in the middle, you can imagine I'm going to get a focus of the pressure wave, because from each crystal you would have sort of a circular pressure wave coming out, right? And then when you add them all up, that's the wavefront that you see. And so we'll phase the pressure waves of these such that we produce a focused beam, right? And we can choose where that is. So we have essentially the voltage for each crystal being supplied by an independently programmed input. And we'll start this voltage, this expansion a little bit earlier than this one in the middle. And you can create essentially, just like if you're dropping pebbles in a pond, those waves would meet at a certain place, at a certain depth or distance away, and that would be your focal point of the highest pressure that you see in there. Right? And so, this programming obviously is done now digitally. You can do it very precisely. You can set this focal distance by changing the phase to a certain extent, obviously. And you can do the same thing in the orthogonal direction. So if we had a stack of these such that we had a 2D transducer, we can change the phase as a function of depth in this picture, right? And focus in the slice direction, which is what you're asking for. Normally, that transducer is used to make a 3D picture by rastering in 3D around in the object. Okay. Okay, so worth remembering these coordinates, that axial resolution this way, lateral resolution side to side, and then the elevation or slice thickness is this way. The dimension of the crystal in the elevation or slice dimension will give you a different sort of profile here and a different optimal location for this, slice, the thinnest slice that you're going to get, right? Okay, so let's see, what time are we at? Oh, I'm going to stop. We'll start here next time. But looking ahead, this is how it's actually done. Is you put out this little burst pulse, right? That's short. It's going to travel along, and if I have two boundaries in the sample, it'll reflect off the first boundary and then reflect off the second boundary. And so our 1% signal is coming back towards us, right? And we turn this into receiver mode and we hear these echoes. So you go boop, boop, and then you listen and you hear boop, boop, and you know, right, that, oh, I'm sorry, that was not the correct model. You go boop, right? This one pulse on this diagram. So you go boop, and then you listen and you go boop, boop, and you know that thing reflected off two objects, right? And the distance in time between those two objects is proportional to their distance in space, okay, given the speed of sound and everything. Okay, so we'll start there on Thursday.